Hello lovelies, in this video we're going to be going through some fundamental core calculations for your A-level chemistry. Now we're going to be going through loads of examples here, so kind of like mole equations, we're going to be going through water of crystallization. You can use the timestamps to jump to the bit that you're looking for, but we've put this all together in one big video because this is core to understanding all of the things that come later in chemistry. If you're confused about some of the algebra, then go and watch the previous video where we talk about like the math skills that you need for this. But if you're struggling with later on some of the bigger equations later on, then this video will help you get the fundamentals down and absolutely sorted.
So let us now have a look at the fundamental calculations section of this work booklet. So for question 1 here, we're told that a mass spectrometer can be used to investigate the isotopes of an element, and we're asked to define the term relative atomic mass of an element. Now this is a definition which is really important that we learn, so perfect opportunity to make a flashcard for it if you don't have it. There's a few slightly modified versions of it, but I'll give you my preferred one and then you can make a note of that. By all means, if one of the other ones feels a bit more intuitive to you, then use that instead. But the one that I prefer is that the relative atomic mass of an element is equal to the average mass of one atom of an element compared to 1/12 the mass of one atom of carbon-12. So that's the key thing, it's understanding that we're comparing to carbon-12 and we're saying that we're comparing it to 1/12 of the mass of one atom of carbon-12. So here we've got the average mass of one atom of an element compared to 1/12 the mass of one atom of carbon-12. Now, I would certainly agree that that is a bit of a tongue twister. It's not the most easy to learn definition, but if you understand it, understand what they're getting at there, and you make an effort to get that memorised, then it will be just fine, okay? So I'm going to highlight here some of the key words that we have. So it's the average mass of one atom of an element compared to 1/12 of the mass of one atom of carbon-12. Okay, so it's the average mass of one atom of an element compared to 1/12 of the mass of carbon-12. So let's have a look at this next bit. So this is where the calculations are going to come in. So here we're given the mass spectrum of element A, and we've given the percentage abundance of each of the isotopes, and they're all labelled on this little graph. We're asked here to calculate the relative atomic mass of A. Only 1 mark, it's a bit of a challenging one for 1 mark I think here, but we would have seen these questions before, certainly given in tables where the percentage values are given against these masses, and we're asked to calculate it that way. Now with these, the general thing that we need to do is to take the sum of the masses times by the percentages and then divide it by the total abundance. So in this case, because it's a percentage abundance, if we added all of these abundances together, they would add up together to give us 100. And that's the case whenever they give us percentages. So we're going to do the sum of all of the masses times percentages and then divide that by 100. And what we will get there is the relative atomic mass of A. So let's put this into use then. So 74 times 0.89 plus 76 times by 9.37. So here we've done these first 2 peaks. Then we would do 77 times by 7.63. And then we will also add 78 times 23.77. So here we've done these 2 peaks now. And then next up, we would do 80 times by 49.61. So that one there is the most abundant of all of these. And finally, we will do that last little peak, 82 times by 8.73. Okay, so we're going to add all of these together, and then finally, don't forget, we want to divide it by 100. Whew, quite a lot to do there, but let's get out our calculators and see what we get. So calculating that, I get a value equal to 79.0421. So if we were to round that, I would probably round that to 2 decimal places like the rest of the percentages here were given. I would just be consistent with that, and I would say it is 79.04 is our relative atomic mass of A. Next up, we're asked to identify the element of A. So what you want to do here is to find your periodic table and look at the different mass numbers, okay? And we're looking for which element has a mass number close to 79.04. It's not going to be exact because, of course, here we're using a selection of different isotopes. Maybe the isotopes in this instance are different to the ones that we use to determine the periodic table. But we're going to look to the periodic table right now and find what has a mass number of 79.04. So I can see by looking that the one with the closest mass number is going to be selenium, which has a mass number equal to 79.0. So yeah, so there we go, that's how we do it. Let's have a look at the next question. Okay, so here we're told that the gaseous sample of A should be ionised first in order to obtain a mass spectrum of A. Describe how ionisation is achieved in a mass spectrometer and give the reasons why ionisation is necessary. So here you can see it's 5 marks, okay? So we want to give 5 distinct points as to how we achieve ionisation and why we need it. So 3 reasons why ionisation is necessary. So starting with how we achieve ionisation, we can see here we're likely going to get 2 marks for that. So firstly here, I would begin by saying that the electron gun is going to fire high-speed electrons. Those electrons are then going to knock electrons from A, okay? So that in turn is going to ionise A and make positively charged ions. All right, so let's make a note of those. So firstly, we're going to say that the electron gun fires high speed electrons, or you could say high energy electrons. And then we're going to explain that those electrons knock electrons off of A to form positively charged ions. Okay, so that is how ionisation is achieved in a mass spectrometer. Now we want to give 3 reasons why ionisation is necessary. So let's make a note of that next. So 3 reasons why we need to actually do this ionisation in the first place. So firstly, it's because we use an electric field, and the purpose of that electric field is we need to accelerate these particles. Now if they were just atoms and not ions, then that electric field will not be able to accelerate them. So that's our first reason. Next up, we need to then deflect these ions. Now, if they were atoms, then the magnetic field that we use to deflect them would not have an effect on them, whereas when they're ions, the magnetic field can deflect them. So then we need to know that we need to have some way of detecting these ions when they arrive. Now, because they're ions, they can get detected in the form of them causing a current in the detector. So what our sensor or our detector is actually doing is detecting this presence of a current as these charged particles flow into it. Now if these were just atoms, then we wouldn't have a current and therefore we couldn't detect it. So this is why we need to have ions to be able to use them in this mass spectrometer rather than just atoms or molecules. Okay, so let's write these down then. So our first reason why is that ions can be accelerated by an electric field. Next up, we have the fact that the ions can be deflected by the magnetic field, which means bent. Their pathway is no longer straight if they get deflected. And finally, the fact that the detector detects a current that is formed due to that flow of ions. So flow of ions form a current which is detected. Perfect. So those would be our 5 marks for this question. So here we're told that carbon occurs in a wide range of compounds, and we're told that it forms 2 isotopes as carbon-12 and carbon-13. First up here, we're asked to define the term isotope. Now, this is such an important definition. I can't emphasize that enough. We want to make sure that we can flawlessly give this definition. Okay, so for this first part here, we're going to say that an isotope are elements of the same element with the same number of protons, but with a different number of neutrons. So those are our 2 key facts that we need to have there. The same number of protons, but a different number of neutrons. So let's write this down. So our 2 key points are that we need the same number of protons, but a different number of neutrons. And that there will get us a mark every time. So for part 2 of this, we want to explain why isotopes of carbon have the same chemical properties. So in this case, we need to understand that because they have the same number of protons, their atoms will also have the same number of electrons. Now, the importance of them having the same number of electrons is that in their outer shell, they will have the same amount of electrons. So the amount of protons and general electrons is sort of important because it leads us to this place where we can explain that they have the same number of electrons in their outer shell. That is always the thing that dictates the properties. Even if you think to your periodic table, how we organise group 1, group 2, etc., it's with things that have similar properties and also they have the same number of electrons in their outer shell. Okay, so here we're told that the carbon-12 isotope of carbon is used as the standard measurement of relative atomic masses. Define the term relative isotopic mass. So this is really similar to the definition for relative atomic mass. To the point, I would really just replace any instance where we use the word atom with isotope, okay? So here we could say that relative isotopic mass is the mass of the isotope compared to 1/12 of the mass of an atom of carbon-12. So those are the 2 little things that we want to say to get our marks. So the first mark we would get in a question like that is that we are comparing the mass of the isotope compared to 1/12 of the mass of something, and then the fact that it's the mass of carbon-12 is going to be our second mark. Okay, so 2.2, a chemist wants to investigate the number of carbon atoms in graphite, which is still referred to as pencil lead. And I'm sure that we've all done that. We've talked about our pencil lead, but actually it's graphite. So the mass of the pencil lead is 0.42 grams. Calculate the amount in moles of carbon in the pencil lead by assuming it contains only pure graphite. Now, we know that graphite is just carbon. Okay, we learned that at GCSE and it is told to us in this question. So that means that its MR will just be equal to 12. So in this case, when they want us to calculate the amount of moles of carbon in this amount of pencil lead, we're going to say that moles is mass over MR. And in this case, that will be 0.42 grams divided by 12 grams per mole. And we can put that then into our calculator to find the number of moles of graphite in this case. So here I make that 0.035 moles. So that's the first part there of the question. In part 2, they want us to calculate the number of carbon atoms in the pencil lead. Now here we need to understand that to find the amount of, let's say, stuff, so whether it's atoms, whether it's molecules, electrons, anything, we times the moles by Avogadros number. Okay, so in this case, to find N, the number of atoms, we're going to times the moles by Avogadros constant. It's a really clever number, Avogadros constant. If you think, I always like to think of 1 mole as being a word that we use in a similar way to how we use the word a dozen. You know, we use that all the time in day-to-day life, a dozen. We know automatically it means 12 of whatever we're talking about. Now, if we have a mole, it's very similar. It actually means that we have 6.02 times 10 to the 23 amount of stuff. And seeing how horrible that number is, I'm sure you can understand why we have just changed it to just make it this nice little constant, and instead we refer to it as moles. So in this case, the amount of moles was 0.035, and Avogadro's constant, as I mentioned before, this is something given to us in the data sheet, so don't worry if you don't remember it. It's generally 6.02 times 10 to the 23, but do check your data sheet because different exam boards might use different numbers of decimal places to sum it up. So don't worry if you've got a slightly different one. So timesing those together, I get my answer to be 2.107 times 10 to the 22 atoms. And there we go, that would be our answer. So we're told that the explosion at nuclear power plant in Chernobyl released a radioactive isotope of iodine with the relative isotopic mass of 131. And to start off with here, this question wants us to define the term relative isotopic mass. And just like relative atomic mass, we've seen this one comes up again and again and again, so it really is a definition we just want to get to grips with. And the definition of this is that it's the mass of the isotope compared to 1/12 of the mass of one atom of carbon-12. And that is just the definition that we just want to get down and get memorised and just be able to make easy marks on whenever it comes up in a question. Okay, so it is the mass of the isotope compared to 1/12 the mass of an atom of carbon-12. Okay, state the difference between isotopes of an element in terms of fundamental particles. Now here the key thing is that they've asked for the difference. They haven't just said compare them like questions often have. We just want the difference. And remember that that key difference is the different number of neutrons. Protons stays the same, but it's the number of neutrons. Now you could be tempted as well here to say, well, they have different masses or different mass numbers. But remember, this question asked for it in terms of fundamental particles. So although it's correct that they have different masses, it isn't their difference in terms of fundamental particles. So here our solution would be that they have different numbers of neutrons. Okay, so next up we're asked to complete the electron configuration of iodine. So to do this, I would first go to the periodic table. If you look up iodine, you can see that it has an atomic number equal to 53. Now 53 is going to be the number of electrons that an atom of iodine has. So we know that it has 53 electrons, and that's going to be our little starter fact. At the moment here we have 1s2, 2s2, 2p6, 3s2, 3p6. So in total there we have got up to 18 electrons. We need to get all the way up to 53. So we can then next up do 4s2 and then 3d10, and then we can do 4p6, and then once we've done that we can go to 5s2. Let's check how many electrons we have at the moment. So up to this point we had 18, so then we had 20, 30, and now we've got 38, so we still need 15 more electrons. So after the 5s2 we're back to the D subshell, so we now have the 4d10 subshell. So that brings us up to 48 electrons. We need 5 more. We're next on to the 5p subshell. So we need 5 electrons within that p subshell. Not the full 6, just 5, because then that gets us up to our full amount of 53 electrons. So that there would be our electron configuration of iodine. So next up we're asked to write the subatomic particles in an atom of iodine 131 and in an atom of iodine 127. Now the important thing here is to remember that this 131 and this 127 refers to the mass number of both of those two things. Now they're going to have different numbers of neutrons, as we said earlier, but the protons will stay the same. Now in this table here, they've told us the number of electrons in each of the iodines, and they're the same in both, and that's because they're going to have the same number of protons in both. Now don't forget that when we have an atom, just like we have atoms in this question, the number of protons is equal to the number of electrons. So in this case, we can simply say that we have 53 protons in both of them as well, which supports the fact that they're isotopes. Because don't forget, in an isotope you have the same number of protons but a different number of neutrons. Next up though, we need to work out the number of neutrons. So if in iodine 127, we know we have 127 particles in the nucleus, which are protons and neutrons, and then we subtract the amount of protons that we have, the number that we're left with will be the number of neutrons. So if we do 127 and we subtract 53, we will get the number of neutrons, and in this case that is 74. Likewise, we're going to do exactly the same with the iodine 131. We're going to subtract the number of protons and we'll be left behind with just the number of neutrons. So that then leaves us with 78, and that will be the number of neutrons that that particular isotope has. And this table here really supports our answer from 5.2. You can see that the only difference in terms of subatomic particles between these isotopes is that they have different numbers of neutrons. In interhalogen compounds, the halogen atoms are bonded together covalently. The interhalogen compound X contains a certain amount of fluorine, 42.8%, and also 57.2% of iodine. So here we're asked to find the molecular formula of the compound X, given that the molar mass of this compound X is 222. So in this question there's going to be two parts. First, we're going to want to find the empirical formula, and then once we have that, we're going to use the empirical formula and the molar mass of the compound to find the molecular formula. So let's get started. So to find the empirical formula, I would start off by writing like a little table almost of the fluorine and the iodine. And I will write the percentage by masses next to each of those. So I know that I've got 42.8% of the fluorine, and 57.2% of iodine. The next thing that I would do in my little table I'm making here is write down the MRs of both the fluorine and the iodine. And looking it up in a periodic table, I can see that fluorine's MR is 19 and iodine's is 127. So now I'm going to divide each of those by each other. So I'm going to do the mass percentage divided by the MR, because what that's essentially giving me is the number of moles, which is the mass over the MR. But because it's the percentage by mass, not the actual mass, it's not giving you the actual amount of moles, but it will still be a good ratio of moles. So here, if I do 42.8 divided by 19, I get 2.253. And for the iodine, if I do 57.2 divided by 127, I get 0.450. So what I've got there now is a ratio between the moles of fluorine and iodine, but it's not in its simplest whole number ratio. And that's what we're going to want to do next, to get it in that simplest whole number ratio. Now, the way I generally choose to do this, and it will work majority of the time first time, is I'm going to pick which of these is the smallest and divide each of these moles by the smallest number. So in this case, I can see that the smallest of the two is the 0.450. So I'm going to divide both of the numbers by the 0.450. Now that will leave for the iodine just 1, and for the F, it will leave us with 5. So by doing that there, I have got a formula, an empirical formula for this, of IF5. And of course you could write it as F5I, it just looks better like this. It's a bit more formally correct to write it in this way. But you'd get the marks regardless. So now we have the empirical formula, we can use this to work out the molecular formula. So the way to do that is just work out the MR of the empirical formula. So we'll do that by taking the fact we've got 1 iodine, which is 127, and adding on 5 of the fluorines. So if I do that, 127 plus 5 times 19, I get an answer of 222. Now that is the MR of the empirical formula. If you look at the actual molar mass of the compound that they've given us in the question, you can see that that is also 222. And what that tells us is that the empirical formula is actually the same in this case as the molecular formula. So our answer to part 1 here is IF5. So for part 2, they want us to state the shape of this compound. So the fact that we would use here to sort of work out the shape of this compound is we would have a think about the bonding. Iodine, of course, has 7 electrons in its outer shell. So let's just draw that up there. We know it's bonded to 5 fluorines. So we've got like a little fluorine there with its little dots. Got another fluorine here. And the reason why I'm doing this is if we're ever unsure of the bond shape, you can do the dot and cross diagram and then have a look at the central atom within this bond and see how many bonded pairs and how many lone pairs there are. So here I can see that I have got 5 bonded pairs and I have 1 lone pair. And there's a specific shape that corresponds to a substance which has 5 bonded pairs and 1 lone pair around that central atom. The name of this is square pyramidal. So that is the answer to that, and that is my top tip to deal with these. Of course, you need to go away and learn all the shapes and when we would see that shape, But once we know how many bonded pairs and lone pairs each shape corresponds to, you can just apply it to any question. Mass spectrometry can be used to identify isotopes of an element. State why isotopes of an element have the same chemical properties. So this is a really simple answer, and it is one that you definitely want to have memorised. The reason why isotopes have the same chemical properties is because they have the same number of electrons in their outer shell. So the same number of electrons in their outer shell. Alternatively, you could have said that they have the same electronic configuration. Okay, so part 2 here. Particles with the same mass and velocity can be deflected by different amounts in the same magnetic field. Suggest one reason for the above statement. So if we think about what things might affect the extent to which something is deflected and how much it's deflected in a magnetic field, obviously we could see that the mass will affect it and the velocity will affect it as well. But there's a few other things as well that might affect it. I think here the best example for you to give would be that if the particle has a different charge, then it will be deflected by a different amount. So different charges would be a great answer for this one. So for part 3 here, we're asked, how does the detector in a mass spectrometer enable the abundance of an isotope to be measured? Now, this is a really great question if your exam board needs to know about mass spectrometers and how they work. So the answer to this is every time that an ion hits the detector, they will cause a current. And basically the bigger current that is made, that's going to correspond to the bigger abundance. And so when we record a bigger current, we know that there's a greater abundance of those particles. So our answer to this, for 2 marks, we're going to give 2 points. We're going to say that the ions hit the detector, causing a current. And also we're going to say that the bigger the current means that there's a bigger abundance. And that would be our solution to part 3. We're told that a mass spectrum of a sample of copper showed 2 peaks at MZ63 and at MZ65. So this is quite a tricky one, in truth. And what I would recommend that we do is that we class the abundance of the isotope with MZ63 as being X, and we class the abundance of the isotope with MZ65 as being Y, let's say. So if we were to work out the relative atomic mass of copper, what we would normally do is we'd multiply the abundance of each isotope by its mass, add them all together, and then divide by the sum of those abundances. Quite often it's percentages, but here, because we haven't had that explicitly stated, we're just going to call them X and Y rather than being like the percentages that add up to 100. So here, let's try this then. So we would do 63 times by the abundance X, and then we're going to add 65 times by the abundance Y, and then we're going to divide it by the total abundances, so the sum of them, which is X plus Y, and we're going to equate that to the atomic mass, which in this case we know is 63.5. So now that we have this, we can use our algebra skills to rearrange this and get all of the X's together and all of the Y's together ultimately. So doing that, I would start by multiplying through by this denominator. So I end up getting on the top 63x plus 65y, and then that's going to be equal to 63.5 times by the x plus y, which ends up being 63.5x plus 63.5y. Now I'm going to get all of my x's together and all of my y's together too. So I can do that by, let's move the x's over to the other side. Let's subtract 63x from each side. So by doing that, I'm just left with 65y over on the left, and I'm left with 0.5x plus 63.5y on the right hand side. So next up now, I am going to move my y's over to the left hand side. So here I'm going to subtract 63.5y from each side. That leaves me with 1.5y equals 0.5x. So now what I can do here is I can see that I have 1.5 y's for every 0.5 x's. Or alternatively, I could rewrite that as like the simplest ratio in whole number terms. And I can rewrite that as 3y equals just 1x. So when we're talking about these two different isotopes, which let's say are the ones with the MZ63 and the MZ65, we said that the abundance of the 63 isotope was X and for the 65 was Y. Well, we've just said, haven't we, that X is actually the same as 3 Ys. So we could, in theory, replace our X with 3Y. The Y is still Y. And now they're both in terms of the same thing, okay? This is the important thing. We have a ratio here because we can say that we've got 3Y to Y, which simplifies down to just being a 3-to-1 ratio. So that means that we have got 3 times as much of the 63 isotope than we do of the 65 isotope. And if we think of what the mass number was, well, it was 63.5, it makes sense that we're going to have more of the 63 isotope than the 65 isotope anyway. So, looking back at the question, they wanted the ratio of the relative abundances of the two isotopes. As you can see here, the answer is a 3-to-1 ratio in terms of the 63 to the 65. That's good work. So here we're told that the mass of 1 mole of hydrogen atoms is 1.0078 grams and the mass of 1 atom of hydrogen is 1.6734 times 10 to the minus 24 grams. And here we're asked to calculate the value for Avogadros constant. Obviously this is an odd one because we could just look up in the datasheet what Avogadros constant is, but this one's really testing your understanding of what it means. So here we can see that we have 1 mole of hydrogen atoms has a mass equal to 1.0078 grams. And we also know what the mass of each individual atom is as well, okay? So we know that 1 mole of hydrogen atoms is the same as n atoms, which is some amount, which is Avogadros' number. So here we can say that the mass of 1 mole of atoms is going to be equal to n times by the mass of 1 atom. So of course we have numbers for these, don't we? So let's substitute those numbers in. So we've got 1.0078 grams is equal to n times 1.6734 times 10 to the minus 24. So now we've got a little formula that we can rearrange to find n. So we can do that by dividing the 1.0078 by the 1.6734 times 10 to the minus 24, and that simply leaves us with our answer, which to 5 significant figures is 6.0225 times 10 to the 23. So next up, we're told that the 1 isotope of magnesium has a relative mass of 25. And remember that relative mass tells us the amount of mass that 1 mole has, okay? So we know that 1 mole of magnesium is equal to 25. But then we're asked to find the mass in grams of a single atom of this isotope. So now what we want to do is remember that 1 mole is the same as 6.023 times 10 to the 23 atoms. And so that is also what's equal to that 25 grams. So now we need to think, well, if we had 1 atom, what mass would that have? And we can do that by dividing the 25 grams by Avogadros' number, and that would give us the mass of a single atom. And that in this case here leaves us with 4.15 times 10 to the minus 23 grams. And that there is the mass of a single atom of this isotope of magnesium. So for part 2 now, we're told that we're given percentage abundances of 2 isotopes out of 3, and we're asked to find the abundance of the third isotope. So I think in this case here, it's fair to see that it is a percentage abundance. And so in that case, we need to think, okay, so if we have 2 different abundances, we know that all of the abundances have to add up to 100%. So I would do 100% minus the 68.60% minus the 10.11%. And what we're left with there should give us the abundance of that third isotope. So that gives me 11.29%. So finally now, we're told what the relative mass of this sample is. We're told that it's 24.33. And we're asked to find the mass number of the third isotope. So this is a tricky one because we have to almost work backwards. We're not being asked to find the relative mass, we're told it. So this is where we're going to want to use a little bit of algebra, okay? So let me show you what we'll do. So as with all of these relative mass ones, what we want to do is take the mass number and times it by the abundance and then add those all together. So in this case, I've got 24 times 78.60 plus 25 times 10.11 and then plus x, because we don't know that final mass, times by its percentage 11.29. And we divide all of those by the sum of the abundances, which in this case, because these are percentages, is 100. And then we put it equal to the mass number, so 24.33. Now we need to rearrange this, okay? Because eventually we want to get x as the subject. So if I do the 24 times 78.60, I get 1886.4. So just taking it step by step there. Then I do the 25 times 10.11, and that ends up giving me 252.75. So again, take your time with these, don't rush it. And then the last bit, we don't know what x is, so I'm just going to write that as 11.29x. Now that's all over 100, so I'm going to times through by that 100, and I get that's equal now to 2,433. Now we need to do a bit more algebra. So subtracting those highlighted numbers over to the other side leaves me with 11.29x equals 293.85, which if I divide by the 11.29, it's going to give me what my x is. And here I get 26.03, which if I get that just as a whole number, rounds to 26. So the mass number of this third isotope is just 26. So here we're asked to consider the following reaction and to answer the questions given below. We're told that barium chloride reacts with sulfuric acid to produce barium sulfate and hydrochloric acid, and that's shown here in this reaction. Next up, we're asked to calculate the percentage atom economy for the formation of barium sulfate. So the important thing here is we know that we want to make barium sulfate, so that is our useful product in this case. So here let's get started by writing down our equation for the percentage atom economy. So here to calculate this, we're going to take the MR of the desired product, so in this case barium sulfate, and then we're going to divide it through by the MR of all of the products. So we're going to add them all up, and then we will end up multiplying through by 100. So in this case here, we can see that the MR of barium sulfate is equal to the MR of 1 barium, which we'll look it up in the periodic table. We can see it's 137.3, plus the MR of sulfur, which is 32.1, and then plus 4 times the MR of oxygen, which is 16. So tallying those all up together, we end up getting a solution for the MR of barium sulfate of 233.4. So now let's get the MR of HCl, and then so that is going to be 1 plus 35.5, which gives us 36.5. Now we can see here that substituting those in, we get 233.4 divided by all of the products. So that's 233.4 plus 2 of the HCl's. So 2 times the 36.5, because you have to take that into account. Then times it by 100, and then I end up getting an answer equal to 76.2%. So that there is the percentage atom economy for the formation of barium sulfate. So now we get to calculate how many moles of barium chloride there are in 312.4 grams. First thing we want to do is get the MR of barium chloride. So it's going to be 137.3 plus 2 times the MR of chlorine, which is 35.5. So we'll put that all into a calculator to work out that MR, and I make it to be 208.3. So we know the mass is 312.4 grams. So now we can use our standard equation of moles is mass over the MR to work out how many moles of barium chloride there are. So tapping into the calculator, we will do 312.4 divided by 208.3, and I make that to be equal to 1.5. So I make it 1.5 moles. And here we're asked to calculate the maximum amount in moles of barium sulfate which can be formed in this experiment. So to work this out, we really need to go back to our balanced equation right at the beginning. And you can see that we have a ratio between them of 1 to 1. And this is these balanced equations, they're so helpful. Okay, so because it's a 1 to 1 ratio, we have the exact same number of moles of barium sulfate as we do barium chloride. So that is the maximum amount of moles of barium sulfate that can be formed. So now we're asked to find the maximum mass of barium sulfate. So to do this, it's really going back to our moles is mass over MR equation, but rearranging it. So here we want to find the mass. So that's going to be the moles times by the MR. Now the moles we've just said is 1.5, and the MR we worked out earlier on, so we can just reuse that. And that was equal to 233.4. So to work out the mass, we are now just going to multiply together 1.5 moles times by 233.4, and I make that to be 350.1 grams. We're told that a student found that only 152.5 grams of barium sulfate was produced at the end of the reaction, and we're asked to calculate the percentage yield of barium sulfate. So to do this, let's start by just writing down the formula for percentage yield. So percentage yield is equal to the actual yield that you actually get divided by your theoretical yield, which is what we could in theory our maximum mass be. And then we multiply that through by 100 to get it as a percentage. So in this particular case, the actual yield from the question is 152.5, and the theoretical yield from the earlier part was 350.1 grams. So let's substitute those in and times by 100, and I end up getting for my percentage yield an answer of 43.56%. And that there will be the percentage yield of barium sulfate for this question. Good work, let's try the next one. So this question here starts quite simply with a definition question, where we want to define the term mole. So when defining a mole, we've got a couple of different options that we could give, okay? So I'm going to tell you them both, and then you can decide which is your favourite. So firstly, we can say that 1 mole is the amount of substance which contains 6.02 times 10 to the 23 amount of particles of that substance. So that number is referring to Avogadros number. And that is certainly what a mole is. It's an amount of a substance which contains Avogadros number amount of particles. So that's one definition. Another comes back to carbon. So we could also say that 1 mole is the amount of substance which contains as many particles as there are atoms in 12 grams of carbon-12. Now, both of those definitions are very good definitions that should always get you the marks in an exam. So if one of those you prefer over the other, always feel free to do that. But we've got those written down there, so if you didn't know them, you can always add them to your notes now. So next up, we're told that we have 30 centimetres cubed of a gaseous hydrocarbon, CxHy, and it's reacted with 150 centimetres cubed of excess oxygen gas. The final volume of the gaseous mixture was 135 centimetres cubed. So when the above mentioned gaseous mixture was treated with concentrated aqueous hydroxide, this reaction reduced the gas volume to just 75 centimetres cubed, okay? Everything done here was done at room temperature and pressure, so 298 Kelvin and 100 kPa. So to start off with here, they want us to take our sodium hydroxide and react it with carbon dioxide. So that's our first little task here to think, what would that become? So if we were to take some sodium hydroxide and react it with carbon dioxide, we will get 2 products. We would end up getting sodium carbonate and water. Now, it's important that we remember that Na2CO3 is the formula for sodium carbonate, for the very important fact that, of course, sodium has a charge of +1, carbonate has a charge of 2-, so therefore, to balance that and to have them react together, we need 2 Nas, which makes it Na2CO3. And as a knock-on effect, we have 2 NaOHs because of that. So that there is our balanced reaction between sodium hydroxide and carbon dioxide. Now for part 2 though, they ask us to calculate the volume of CO2 produced by the combustion of hydrocarbon CxHy. So to solve this, we need to think of what has happened here. So we know we started off with 30 centimetres cubed of the gaseous hydrocarbon, and we reacted it with 150 centimetres cubed of excess oxygen gas. So that's very important. We know that the final volume of the gaseous mixture was 135 centimetres cubed. So that's what we had after the reaction had taken place, the first reaction, 135 centimetres cubed. So then it says, then the above mentioned gaseous mixture was treated with concentrated sodium hydroxide. And this reduced the gas volume to 75 centimetres cubed. Well, we know that this reaction that we've just written down shows that we remove all of the CO2 from this. So in the beginning, when we had our hydrocarbon, so the CxHy, and it reacted with oxygen, it would have made CO2 and water. Now, we had 30 centimetre cubed of the hydrocarbon to begin with, and 150 centimetres cubed of oxygen. And after, we're left with 135 centimetres cubed of gas generally. Now, because the oxygen was in excess, all of that is gone. So we're going to have some oxygen left, and we would have made some CO2. Water is not a gas in this case. So that final volume of the gaseous mixture, being 135 centimetres cubed, is actually the joint volume of the oxygen that we have left and some CO2. We're told that we then react that 135 centimetres cubed of gas with some sodium hydroxide, leaving us with just 75 centimetres cubed of gas at the end. So we know that in that reaction, what has been removed is the CO2. So the difference then between that 135, that was the volume of a mixture of CO2 and oxygen, the difference between that and the 75, which must be that of the oxygen, leaves us with the volume of CO2 that we must have had. And likewise there, when it says calculate the volume of oxygen used up in the above combustion, well, we know that we initially had 150 centimetres cubed, didn't we, of oxygen gas? And then we now know that at the end we had 75 centimetres cubed of oxygen gas left at the end. So if we subtract that 75 centimetres cubed from the original 150, that will leave us with the remaining volume of oxygen. So that there is our solution to this bit of the question. So now we're asked to sort of pull all of the information that we have together into this overall equation. So what we've just done has led us into this, and it's going to help us out. So I'm going to start here by writing out the equation, and underneath it I'm going to write down the volumes of each of those gases that we've just sort of found. Okay, so let's get started here. I'm going to just copy up that CXHY plus O2 goes to CO2 plus H2O. And obviously that isn't balanced yet, but we will get it balanced. So from the previous part of the question, we were told that we had 30 centimetres cubed of CXHY. We worked out we had 60 centimetres cubed of CO2 and 75 centimetres cubed of O2 reacted. Now, let's turn this into a ratio. Let's divide by the smallest number, a bit like we would if it was an empirical formula, to get the simplest whole number ratio between each of these different substances. So I can see I have 1 of the CXHY, 2.5 of the O2s, and 2 of the CO2s. So if I now know I have 2 CO2s, I can take a think about that, and I can use that to work out what X must be. Because if I have 2 CO2s, I know that I must just have 2 carbons. And if I have 2 carbons, well, if I go back and look at that original formula for the hydrocarbon, that must mean that X has to be equal to 2. So let's do something similar now. So we've just said that we know that we have 2.5 moles of the O2. And so if we think, well, how many oxygens does that translate to? That means we have 5 oxygens. Well, if we think about what we've just been saying about the CO2 and the fact we have 2 CO2s, that's going to mean we have 4 oxygens overall in those 2 CO2s. So as a result, if we did 5 minus the 4 to see how many oxygens we need left, you can see we have 1 oxygen we need left, and that has to have come from the H2O. That must mean we only need 1 H2O. So that has told us now how many waters we need. And now that we know that we only have 1 water that's made, that means that we only have 2 hydrogens that are needed to make that 1 water. And again, looking to our hydrocarbon here, which is CXHY, that must mean that the Y must be equal to 2. So now we've worked out what our X is, what our Y is, and what our Z is as well. And we can use all that to then write the balanced chemical equation for the combustion of the hydrocarbon. So in this case here, we know now that we have C2H2 plus, and we can write 2.5O2 goes to 2 CO2 plus just 1 water. Or if we wanted to, because maybe we don't want to have a 2.5 for the oxygen, maybe we want them to all be whole numbers for a whole number ratio, perhaps we could also just double everything up. So we could say we have 2 C2H2 plus 5O2 goes to 4 CO2 and 2 H2O. But really, they are all absolutely fine. Either option will be correct for you. So here we're given the mass spectrum of the isotopes of element P, and they're shown here in this diagram below. So here we can see each percentage abundance is given by a peak. First up here, we're asked what is the meaning of the term mass number of an isotope? And the answer to this one is simply that the mass number of an isotope is the total number of protons and neutrons in the nucleus of an atom. So total number of protons and neutrons in the nucleus of an atom. So we're asked to explain why there are 4 different peaks in the mass spectrum of this sample. And this is a really important bit of information, but because what each of these peaks represent is a different isotope. So the fact that there's 4 peaks tells us that we have 4 isotopes in this sample. Okay, so next up we have to do the actual calculation to find the relative atomic mass of element P. And to do that, we need to take each of the individual atomic masses and multiply them through by their percentage, and then add them all together and divide by 100, and that would give us the relative atomic mass of element P. So what we need to do here is 0.56 for this peak here, times by 84, and then we add on the next peak. So that is 9.86 times 86. And then we do it for the next peak as well. So we add on 7.00 times 87. And then finally we add on, we've run out of space, but it's okay, this peak here. So that is 82.58% times by 88. And we're going to add all of those together and divide our final amount by 100. So I need to go to my calculator here myself. Let's work it out. So here I end up getting 8,771.04 divided by 100, which will give us 87.7104. Now that there is our relative atomic mass of element P, and I would round that probably to 1 decimal place, unless they specify something otherwise. So our answer there, 87.7. And if we take a moment there just to check, does that make sense? If we look up here to our little table, you can see in our graph, most of the isotopes have a mass of 88. So it makes sense that of all of those different masses of isotopes, the relative atomic mass is closest to that mass with the biggest abundance. Okay, so now that we've identified the relative atomic mass of this isotope, they ask us to come up with the electronic configuration of it. So to do this, we're going to want to have a look at the periodic table and see if we can work out what that element must be. So if we take a little look at the periodic table, I can see that the element with the closest mass number to this is strontium. And strontium, if I look in the periodic table, has a mass number of 87.6 and it has a proton number of 38. Now remember that proton number or atomic number, that is the same as the total number of electrons that it has as well. So when we need to give the electron configuration of element P, we need to think that it has 38 electrons and start from there. So we've got strontium, and we want to give its electronic configuration, so we know it has 38 electrons. So let's get started. So we've got 1s2, 2s2, 2p6. So at this point now we have 10 electrons. And then we have 3s2, 3p6, and then 4s2. So there we've got another 10 electrons there. And then we are going to have 3d10, which gives us 30 electrons. And then next up we need 8 more electrons, okay? So we're going to go 4p6, and then once that shell is full, we will go 5s2. And if we were to tally up all of the electrons that we have now, 20, 30, 36, 38 electrons. So that there is our electronic configuration of strontium, which is element P. So now we're told in a mass spectrometer, the relative abundance of each isotope is proportional to the current. Explain how this current is generated. So in simple terms, what happens here is we have our positive ions. They are going to be moving towards the negatively charged detector plate. So we can imagine we've got all these positive ions and they are flowing towards this negatively charged detector plate. And when they hit this detector plate, what we will see is that this positively charged ion is going to gain an electron. So essentially electrons are going to leave the detector plate and go to the ion. And so this gaining of an electron discharges the ion and causes a current to be produced. So the more ions that hit the plate, the more electrons will be released from the detector plate, and therefore the bigger the current that there is. So let us have a look here then. So we've got 2 points, 1 and then 2 to get our 2 marks. So the first thing we want to say is that the positively charged ions flow towards the negatively charged detector plate. And once they get there, what will happen is that the positively charged ion will gain electron at the plate, and then this causes the current. So there we go. We have got to the end of this big pack of exam style questions. I really hope that you feel like you're getting to grips with these topics now. And most importantly, I hope that you've really got a feel for what the exam questions are going to be like, so that you're not going to get surprised when they come up when you do your first set of exams. Good work, and I will see you over at the next video.
Ouch! This is why in some videos I explain scratches.